And there's a theorem that this irreducible representation of W, which index the strata, is exactly the union of this set's irreducible P of W over all primes or 0. So this gives another reason why this set of strata is finite. So then you can interpret this equality. You can saying that the set of strata can be viewed as a union of the set of unipotent classes for various P. So this union, if you regard both sides as a subset of the set of irreducible representation, then this union is taken in that set. So for example, if you take if you take, there's a group, one of the most interesting groups in the world is a group of type E8. So this is a group of dimension 248. And in this case, just to tell you what this strata look like, so there are 70 unipotent classes over complex numbers. If you take this group in classic 2, it will have 74 unipotent classes. And if you take this group in classic 3, it has 71. But the number of strata is actually 75. And how do you see that? So there's a set with so there are 70 classes in classic 0, and then you have to add 4 classes in classic 2, which are not in classic 0, and also 1 class in classic 3, and this forms the set of strata. So now it turns out that every stratum contains at most one unipotent class, conjugacy class. But a stratum contains, actually does contain unipotent class in some characteristic. So if you change the characteristic, the so if you change the characteristic, the stratum will contain unipotent class. Of course, in GLN, this statement is trivial, but I state this interesting statement in other types. So, for example, here is an example. If you take a symplectic group, in fact, I don't know. Did I run out of time already, or not? I don't know what's the time. Anybody? I don't know how time. What's the time? 1 minute? Okay. Yeah, so in a symplectic group, as before, there are 5 strata, and if characteristic is different from 2, then 4 strata contain unipotent class, and 1 stratum doesn't contain unipotent class. It is a class of this matrix 1 minus 1 minus 1, 1. But if characteristic is 2, then every stratum contains a unipotent class. And in GLN, any stratum contains a unique unipotent class. Okay, maybe that's it. So.
Thank the speaker very much. Any questions or comments? Okay. Here.
So, Professor, can you please provide some motivating examples as to why do we consider homologic groups of the Springer fiber?
No, what? Can you repeat?
So why the homologic groups of the Springer fiber has something to do with this stratification?
Well, just because it works, so it works. So others, so this definition works. So why not use it if it works? Yes.
Okay, thanks a lot. Due to time constraints, we only just one question to ask. Thank you very much. Thanks.
Okay.
Now, let's welcome our second speaker, Professor Peng Shan. The title of her talk is Monoid Categorification of Skin Algebras. Thank you. Welcome.
Thank you very much. I'd like to thank the organizers for giving me this opportunity to speak at this great occasion. So I will talk about monoidal categorification of scaling algebras, and this is based on joint work with Dylan Allegretti and Hoon-Kyun Kim. So maybe let me start by explaining what is a categorification. So roughly speaking, categorification of an object just means you have some higher structures which realize your object A as a shadow. So for example, take a finite dimensional vector space, and then you can take its dimension that gives you a number, and you can say this number is the shadow of this vector space. And then you have some more refined version of this where you take a graded vector space, which is just a direct sum of finite dimensional vector spaces, and then you can take the dimension by remembering the dimension of each of the pieces and then this gives you some Q number where Q is just a variable. So it gives you some Laurent polynomials in Q, which remembers the dimension of your graded vector space. So more generally, the word categorification comes from this notion of category, which is a mathematical structure consisting of objects and morphisms. And assume your category have some sort of exact structure. Say you have a Boolean category with some short exact sequences. Then you can perform the construction of what is called a Grothendieck group. This produce out of your category a Boolean group, which is just a free abelian group generated by the isomorphism classes of objects in your category. And then you mod out the relation where if you have an object which is an extension of two objects, you just say the class of this object is the sum of the two sub or quotient objects. So roughly speaking, this gives you a Boolean category which only remembers the size of your objects in the category by ignoring other informations. And sometimes if you, well, okay, so you can see that backwards saying that this category provides a categorification of this abelian group. And sometimes you want to do some linear algebra, so you want to have a vector space instead of a Boolean group. So you can just complexify your Grothendieck group by changing the coefficient to complex numbers. This gives you a vector space. And if you want to do algebra, so what is an algebra? It's a vector space with a structure of multiplication. And then you can categorify them by putting a monoidal structure on your category. That is, you're allowed to multiply objects in your category. And then suppose it behaves well with these exact structures on your category, then it descends to the Grothendieck groups and give you a multiplication structure on this vector space, which produces you an algebra. So the thing to take back from this slide is basically a categorification of an algebra is provided by some monoidal categories. Now let's look back at our initial example. So what were we doing? You can consider the category of all vector spaces with morphism just linear maps, and then take its Grothendieck group, and this produce you the trivial algebra, which is just C. And then you have tensor products of vector spaces, which gives you the multiplication on C. But you look at this, and there's something particular happening, that if you take a vector space, which is an object, its image in C is not some arbitrary thing. It must be a positive integer, right? The dimension of a vector space is positive. And you have something similar for the graded vector spaces. So more generally, if you have a monoidal abelian category with some suitable finiteness condition, and then you take its Grothendieck group, you have an algebra, then a basis of this vector space is spanned by the classes of simple objects in your category. And these bases have a positivity property in the sense that if you multiply the classes of two simple objects, you will get a linear combination of simple objects whose coefficients are positive numbers, positive integers. Why is that? Because if you do the convolution in your category, you still get an object in your category, which is built up from simple objects. So you descend to the Grothendieck group, this coefficient, which I wrote as aijk here, is just encoding how many times the simple objects appearing in that tensor product. Okay, and so why are we talking about this and what categorification is good for? There are two sources of motivations from, let's see. There's one, let me just say, there's one motivation from quantum topology. So when people study knot theory, you study knots in S3. And then we know that Jones polynomial is an important invariance for knots. And then Kovanov gives some categorification, well, produce some more refined invariance, which you can think of it as a categorification in the sense we just produced. So we just discussed, it's like a complex of vector spaces, and then if you take its dimension, it produces you some Jones polynomials. And then Jones polynomials generalized on one hand by Witten, Reshtiky, and Turayev. They construct invariants of 3 manifolds and constructed some 3D TQFT. And this is also a place where people are currently very, well, there are many works of categorification of this construction happening in the last, I don't know, for maybe, 30 years or more than that. And so this is related, for example, to categorification of quantum groups. And this was first appeared in a proposal of Crane and Frankel. And then it was pursued, the constructions of categories was pursued in the work of many mathematicians like Kovanov, Lauda, Rugier, and many people that I don't have the space to cite here. For example, this morning, Vivek Shende just gave a very nice talk on how to use Fukaya categories to categorify things related to this. And then there's another direction to study invariance of 3 manifolds, which is called skein modules. And in particular, you can consider some skein algebras. This was introduced by Przybylski and Turayev in the 1991s. And then the categorification of which is the topic of my talk today. Okay. And on the other hand side, in representation theory, categorification also plays a very important role. So as Professor George Lusztig mentioned in his talk yesterday, he constructed this categorification. Well, he didn't formulate in this terminology, but basically he constructed the categorification of the positive part of the quantum group using some sheaf categories, some derived category of constructible sheaves on representation of quivers. And there's a convolution structure on this category which makes it monoidal. And then in this category, there are some very distinguished objects which called intersection cohomology complexes, and their image in the Grothendieck group provides precisely this canonical basis. And this was the origin of this basis. And these bases have many important applications in representation theory. For example, they're extremely important for computing character formulas for symmetric groups over a field of characteristic P when P is large enough, and also for Haeckel algebra as roots of unity. So there's some important work of Grochnowski and Ariki addressing this. And then the idea of categorification of Kac-Moody algebras was further developed by, for example, there's very important work of Chang and Rugier where they produce some refined notion of SL2 categorification and use it to prove an important conjecture of Bu-Hu-Wei on a abelian defect group conjecture for representational finite groups. Okay. And so the categorification we're talking about today is roughly in this style. You use some kind of sheaf categories on variety to produce a categorification of your algebra. So the main result at a glance is the following. You take a genus 0 curve with n plus 3 boundary components. So I denoted that as 0, n plus 3. And then one can consider its skein algebra. And our results proves that there exists a monoidal category of equivariant causal perverse coherent sheaves. These are some complicated terminology, but basically some categories of sheaves on a space introduced by Braverman, Finkelberg, and Nakajima. And this produced a monoidal abelian categorification of the skein algebra. And in particular, you can consider the simple objects in this category provides a positive basis of the skein algebra. So the existence of a positive basis has been conjectured by Dylan Thurston in 2014 and has been studied by many people in many different ways. And so we provide a new categorification of this algebra. Okay, maybe let me give you more detail on the content of this theorem. So what is a skein algebra? So you take S to be an oriented surface of genus G and with n boundary components. And then you can consider the following space of, which is a free module over the ring of Laurent polynomials in A. So A here is a quantum parameter. You should think it's roughly Q before. And it is spanned by isotopy classes of framed links in the three manifold S cross the interval 0, 1. Okay. And then on this space, you can put an algebra structure just by superposition. So you have your surface cross the interval 0, 1, and then you can just stack it onto itself and take unions of all the links inside it. And then, so this forms an algebra. And what is the Kaufman-bracket skein algebra? This is the quotient of this algebra by the so-called skein relations, which is like locally, if you have a crossing like this, and then you just replace it by two ways of resolving it, either like this or like this, and then by putting some quantum parameters in front of it. And then if you just have a free loop, you can replace it by a squared plus a minus 2. Okay. And then an important result of Przyczynski and Turayev is that they prove this algebra, it quantizes the ring of regular functions on the character variety, which is the moduli space parametrizing principal SL2 bundles with flat connection on your surface S. Okay, and this can be described in very elementary terms. So by Riemann-Hilbert, it's just the space of group homomorphism from the fundamental group of your surface to SL2, and then you consider them modulo the conjugacy action of SL2 on the target. And if you specialize the parameter in the skein algebra at a equals to -1, you obtain functions on this character variety. And then there's some relative version of this. It's like if you fix some curves around your boundary components, which I denote by delta 1 to delta n here, and some complex parameters lambda 1 to lambda n, and then you can make a quotient of the skein algebra by specializing the value of this free loops delta I to be minus lambda I plus lambda I inverse. And this is a quotient of skein algebra which quantize a closed scheme in the character variety, parametrizing those representations of the fundamental group whose value at this delta I are conjugate to this semi-simple matrix lambda I inverse. Okay, so this is the skein algebra. And then I want to say a word about this Braverman-Finkelberg-Nakajima construction. So they give a mathematical construction of Coulomb branch for 3D n equals to 4 supersymmetric gauge theory. Their input is a reductive group acting on a vector space. And out of this, they produce a complicated infinite dimensional loop space whose definition I'm not giving here. But the important thing is on this space, you have an action of an arc group G of O, and then you can also rotate your loop, so you have a C star action. And then they consider the equivariant K theory on this space RGN. It is a sort of Sternberg variety, and you can perform convolution products on K theory. So this produces you an algebra, and what is remarkable in this case is the commutative algebra. And you can take its spectrum, it gives you a fine variety, and this is what they call Coulomb branch. And this construction naturally comes with a quantization, is that if you turn on in the equivariant group, the loop rotation equivariance, then this algebra is not commutative anymore, and it provides a quantization of the previous algebra. It also has natural deformations. So if on your vector space N with this G action, you have the additional group F acting, commuting with G, then you can also consider equivariant K theory by adding in equivariance for this group F, and this provides you a deformation of this BFN algebra. So our idea is to relate skein algebra to this BFN algebra, this equivariant K theory. But you see immediately the inputs are very different. For skein algebra, you started from a surface of genus 0, well, some surface, and then here the input is a group and a representation. So I need to tell you how do you assign the data of a group representation to the surface of genus 0 and n+3. So what you do is you consider this tube here is supposed to be a sphere with n+3 punctures on the boundary. And then I had the free loop delta i's. And I fixed the Pence decomposition by cutting it at the curves called gamma I. And then to this, I attach a quiver. For each gamma I have a gauge knot of the quiver, and the dimension is 2. So in the picture, I have n of them. And then I have 2 framing vertices at the end. And then I just consider representation of this quiver. So the group will be a product of GI with So GI is SL2, and then I have one SL2 for each of the orange vertices. And then I take the representation of this quiver, which is just the home space I'm writing here. So So some home space between VI plus 1, and each time VI is just the standard representation for the corresponding SL2. Okay. And then there's some commuting action with G, which is just a torus F. It acts on the framing vertices and also by scaling the edges. So yeah, so this construction was following some ideas of Gaiotto in n=2 duality. And then the theorem we prove is that, so we can identify the coefficient range of the skein algebra with the equivariant K theory of the C star rotation and this torus F, equivariant K theory of a point. And so here A is the quantum parameter corresponding to the Q in the C star rotation, and then the others are the parameters in the F equivariant K theory of a point. Then there's the isomorphism of K algebras between the relative skein algebra associated to the surface with n+3 punctures, and this BFN algebra, which is the equivariant K theory, with the Gn and F I explained above. Okay. So in particular, this is an isomorphism over the integral form, so you can specialize A to -1 and obtain an isomorphism between the character variety and the BFN Coulomb branch. And just to end, so this equivariant K theory is by definition the Grothendieck group of the equivariant derived category of coherent sheaves on this space. And in this situation, Cautis and Willems defined a remarkable T structure on this category, which is called causal perverse coherent T structure. Its heart is an abelian category, which we call this PGN. It is an abelian category, and remarkably, it is closed under the convolution product. And so, therefore, as a corollary, we have a monoidal abelian category whose coordinate group is isomorphic to the scaling algebra, and therefore the simple modules provides a positive basis. And just a final remark, so there are other people working on this subject. There are other people looking at scaling algebras, categorification of scaling algebras using a different approach, more similar to Kolanov homology. And for example, there are work by Asaida Przezitsky, Sikora, and Kefelak Wedrish. Okay, and so here are my collaborators. Dylan is there in the audience, and then papers are available on arXiv. Thank you very much.
Thanks, speaker, very much. Any question? Okay, that guy.
Hello, professors. As shown on your slide, that the scaling algebra can be viewed as a deformation of ring of functions of the SO2 character variety. So I like to ask that, what makes the group SO2 so special here? Or are there any similar stories for other groups? Thank you.
Yes, there are other scaling algebra associated to other reductive groups, but what makes SL2 special is this scaling algebra is more explicit. You can describe it in this, using this Kaufman scaling relations, and the others are more subtle to describe.
Okay, more question? Because we have more time. Okay, thanks, speaker.
Thank you.
Let's thank the speaker, all speakers again.
Thanks again to professors and the participation of the audience. I believe the lectures have sparked a lot of thoughts among us all. This is exactly the significance of the mathematics night. As previous years, the International Congress of Basic Sciences this year has also awarded the Frontier Science Prizes with over 100 laureates in the field of mathematics. Next, we will invite 4 award representatives to share their insights on academic pursuit. First, let's welcome Professor Sergei Gukov from the California Institute of Technology, who is the professor of the mathematics and theoretical physics. Welcome to the stage.
Thank you very much. Ciprian, who is another author on the paper that was awarded this FSA award, and I are extremely honored and humbled to be selected for this award. We are very, very grateful to ICBS and FSA Selection Committee for choosing our work. I won't be able to tell you what the work is really about in detail, but it's actually on the same subject that Professor Peng Sheng just explained. It's bridging non-commutative algebra and low-dimensional topology. But I want to tell you a little bit about the style of the work and what it feels to work in this field. In particular, hopefully these remarks could be helpful to young scientists. In general, in my research career, which has been over 20 years, I love building bridges, not just between different areas of mathematics, but between mathematics and other fields, such as physics and string theory in the past, and computer science and mathematics more recently. And hopefully one day I'll be back to Beijing for FSA in information science. So these areas of kind of interfaces between different sciences are extremely fruitful, and there is a lot of bread on a table that's often left at this junction. And even the talk by Peng Sheng that you witnessed a moment ago is also bridging several different areas. So I definitely advise young scientists to go there, but I also want to highlight a couple of aspects which make it fun and interesting. So first, someone could object, hey, Sergey, doesn't it require expertise in 2 different domains to build a meaningful bridge between 2 different areas? And some of the students already expressed concerns that we have a growing body of information that they need to learn. And you would be absolutely right that, yes, it is true that it requires expertise in 2 different domains. And now that I work on computer science and AI and mathematical reasoning, I sometimes see computer scientists who try to build models of mathematical reasoning by having only idea of what International Math Olympiad is about. And of course, that's very far from research level mathematics. And to be fair, conversely, I sometimes see colleagues in mathematics who think that they can master AI techniques in a couple of months, and that's also not true. So it does require a whole PhD in each subject to build enough expertise to say roughly at the level of being able to give a graded course in each given subject. So yes, it takes additional effort, and it is extremely important. I'm not advising to be total novice and trying to build this bridge, so it does require additional effort. But good news is that this is pretty much the only bad news. So yes, it does take additional time to build this expertise, but then there are lots of benefits. First, it's fun to learn new things. It's just easy to explore these new areas, and earning PhD takes only about a couple of years, 3 or 5 years. And once you repeat the process, of course, you don't have to waste time on the same calculus class or basic topology class. So basic classes, of course, serve as foundation for many different subjects. Another benefit of working at the interface of different fields and building these bridges is that people love explaining what they did and discovered. So I was very lucky to receive mentorship from many different people, amazing people in many different areas. Many of them are in fact in the audience, and I'm very, very grateful to them. I was a postdoc of Professor Yao, and together 20 years ago, we were studying geometry of G2 holonomy manifolds. I learned quantum topology for Koля Reshetikhin, who is sitting here in the audience. And if you go and try to build bridges, you'll basically receive many different mentors from different fields, which is a lot of fun. And also, last but not least, this is a great way to build a community of new friends. So by trying to build bridges, you'll acquire more and more friends. So I want to finish these thoughts by also pointing out that recently, together with Professor Yao and team in Tsinghua, we built another bridge. We built a collaboration between Caltech and Tsinghua University at all vertically integrated levels, meaning students, postdocs, and faculty. And if any of you are interested in being part of it, please ask me questions or Professor Yao questions. And again, thank you to BIMSA, thank you to ICBS, and thank you to FSA Selection Committee. It's a great honor.
Thank you for Professor Sergei Gukov. Next, let's welcome Associate Professor Jacob Zimmerman from the University of Toronto to the stage to deliver his acceptance speech. Welcome. So maybe we'll first welcome the Professor Masahito Yamazaki from the Kavli Institute for the Physics and Mathematics of the Universe, University of Tokyo, to deliver his acceptance speech. Welcome. Oh, sorry.
So thank you, everybody. So it's a great pleasure and honor for me to attend this ICBS event. So this is my second event, second time to participate in this event. And it's an amazing event, and I really hope that we will continue. Also, I'm very humbled to receive the Fundamental Science Award. And I'm not going to explain the content of the paper. It's about the relation between mathematics and physics, how to try to understand integral models and mathematical structure they're in from some quantum field theory. But let me try to share one small anecdote, which actually has a lot to do with China. So I started that collaboration when I came back to Institute for Advanced Study in 2016. In April 2016, I have been working on integral models, and Professor Edward Witten, who was the host there, was very excited about the integral models back then. I could visibly see that. and we started talking, and then we also joined forces with Kevin Costello, who is at Perimeter Institute. And it took some time, and then we made the first announcement of the results in 2016. In fact, right in Beijing, because there was no BIMSA, but at Tsinghua University, there was a conference called the Strings 2016 conference. So I'm very pleased to hear that the Strings conference will be held in Shanghai next year, 2026, 10 years after. And but anyway, our first announcement was at the Tsinghua University at 2016. And afterwards, of course, the basic story is there. We started working out things, but then the draft became longer, and we attempted to fill in the gaps in many places. But then there was actually at some point, I encountered some difficulty. I was doing some computations, and I should get a factor of 5, but instead I was getting 2. And it was actually, no, I was getting 2, supposed to getting 2, but I was getting 5. And I was very perplexed. And then I literally spent more than months trying to figure out the factors. And that should work out that way. But eventually I managed to work out the factors correct. And the theory was completed. And we published the papers in 2 papers. One in 2017 and one in 2018. Now, well, of course, that's published in archive, and then we have to send it to a journal. And Professor Edward Witten suggested us to send a paper to the journal called Notices of ICCM. So it's a notices for International Consortium for Chinese Mathematicians. And so I'm very pleased to see that our 2 papers are published in one of the volumes there. And in fact, I noticed that it's actually published alongside with a foreword by Professor Yao on the opening of the ICCM. And there was even an article by Professor Stephen Hawking and Gordon Kane on the future of collider physics and collider physics in China. So I'm very pleased to see our paper getting published there. And so somehow the story has a lot to do with the events in China. So maybe it's not a complete coincidence that I'm coming back here to accept the award awarded from ICBS. Now, over the years, I have been very impressed by the commitment of the China as a country and as a society for the general educations and also the research in mathematics and physics and fundamental science in general. And I'm very pleased to see that, especially in view of what's happening in many different parts of the world. And it's really amazing to see that because indeed mathematics is one of the common languages we can communicate. So once Galileo said that mathematics is a language to describe the world, and in fact, mathematics is really a common language where people with the different backgrounds, cultures, can communicate effectively. And that's that's very much a pleasure for me. Sometimes I run into somebody whom I never met before, but then I can strike a conversation about a particular theorem instantly. And that's the beauty of the mathematics. And I'm very pleased to see that such spirit is well represented by the events of this conference. Thank you very much.
Thank you for Professor Yamazaki. Now let's welcome the last speaker, Professor Chen Gao from the Center for Geometry and Physics of the University of Science and Technology of China. He will share his mental journey from the young talent to where he is today. Welcome.
Good evening, everyone. It's my great pleasure to attend this wonderful conference, to receive the Frontiers of Science Award, and to speak at today's Math Night. My paper studies the J equation and the deformed emission Yang-Mills equation. As mentioned by the previous speakers, my paper also build a new bridge between differential forms in differential geometry and subvarieties in algebraic geometry. This is kind of generalized Monge-Ampere equation. This kind of work goes back to Professor Yao's solution to the Calabi conjecture using the Monge-Ampere equation. I feel very lucky to contribute to this field and also to receive this award. However, honestly speaking, I was not always so lucky. For example, in ICCM 2022, I proposed a route map towards the Hodge conjecture, a famous open problem concerning the connection between differential forms and subvarieties. And however, even though I worked it for several years, the progress has been slow. Fortunately, with the encouragement from Professor Yao and my advisor Xiuxiong Chen and many others, I still keep enthusiastic on this challenging problem. There are many young audience in this room, so I'd like to share some of my feelings to you. The first thing I want to say is that try to dream big. For example, you can dream to be a top expert in your field. Dream for one of the interesting problems in your field, and or you can try to go for the 7 Millennium Prize problems, for example. Second, every big dream starts small. So please start with simple problem first. Even though most of your attempts may fail, any minor improvement matters. It will help you build up the confidence and the skills to go further. Third, try to learn from classical papers in your field. For example, when I was around 20 years old, I studied many breakthrough papers in my field, written by Professor Yao, Professor Donaldson, and other mathematicians. From these works, I didn't see any magic tricks. Instead, I see the hard work, the patience, and the final success. I think this put a big impact on me. Fourth, try to learn from your peers. For example, at this ICBS conference, there are many wonderful talks. By attending them, you can keep your mind fresh, and it may provide some ideas for your own research. Finally, you are among the top students in China, and you are now in a good environment. I truly believe that you will achieve great things in the future. Good luck, and thank all the audience.
Thanks for Professor Chen Gao, and thanks for all the awardees for your sincere sharing, which has allowed us to experience more of the depth and beauty of mathematics. Now the first half of Mathematics Night has finished. About 1 hour later, at 7:00 p.m., we will invite 7 mathematics experts for a panel discussion. Now please move to the house B and C for the buffet. You can get the buffet tickets at the reception desk, or you can also move to A4 for dinner, which doesn't need tickets. See you later, enjoying the buffet.
Methods which you shouldn't forget. You shouldn't, in my opinion, of course, you like I said at the beginning, you all free to make your own decisions and in this and see if they lead to failure or success. But my advice would be to keep studying, keep learning also the good old things to solve mathematical problems, not just start with machine learning.
Maybe if I may add, so there is a slogan I learned from my colleague computer scientist. So before think, then compute. And I think now when we have all this huge computational power that also comes at this very big environmental cost, it seems like a very good slogan. So first we think, and then we use all these amazing tools that we have now and we compute.
Some colleagues, even in theoretical mathematics, like Peter Scholze or Terence Tao, they have used proof verification programs like Lean to check some very technical computations. And I remember Terry Tao even had this vision that at some stage maybe these proof checking algorithms become so fast that one can interact with them in order to find proofs. Do you have any view on that? George? You?
Well, again, yeah, so only thing I can say about these computers, I know one thing, which is that like 50 years ago, I was at Institute for Advanced Study, and Borel was saying that, so we're interested in Lie groups, which can be classical Lie groups or exceptional Lie groups. And Borel was always saying that where we can deal with classical groups, but exceptional groups are extremely difficult. That's a real challenge. But nowadays, the opposite is true. because of computers, you can check various things for exceptional groups first. And that gives you some idea for what happens in classical groups. So the total reversal. So that's something I think is remarkable, yes.
Maybe I can share some of my experience of using Lean. So, yes. I'm currently working on the project where I try to formalize some of my results, and so maybe I just can share what I somehow found out. So first, somehow learning Lean is not that easy, and even installing it on my computer was very uneasy. And also, I think we're still quite far from the moment when computer will start discovering like serious. Of course, it can, like, if you do search, you always can discover something, but I think at this moment it still seems to me we have a few more years of doing mathematics. Yeah, but at the same time, maybe there are like two different sides to what you said. Like, one is to, if you have a result, so should we try to formalize it? And here, maybe I would say that yes, maybe that's a good thing. So imagine that maybe some of you who are, so we have had a situation that you write some lemma and you publish it, and then sometime later somebody asks you a question about it, and you realize, oh no, this lemma is wrong. So it would be nice if, while we are latticing our proofs, we could also on the side formalize them, and then to make sure, okay, so at least I don't embarrass myself.
Andrei?
I think in my mind, the best application of Lean is an instruction. If teaching, like the first proof-based class, it's sometimes hard to explain to students why something is not the mathematical argument why this doesn't hold water. But if they just have to write something that either compiles or doesn't compile, that they have this kind of objective feedback. And so I think for many students, I don't know, I'm speaking in American context, proof is a complicated concept to grasp and to learn it against a kind of a very unyielding component such as lean. I think it's actually very good, I think, in terms of classroom experience.
Right, but now you sort of, I think these answers sound slightly different. When I asked whether we have to incorporate it into the teaching of our students, you sort of said, no, they should not do too much of it, but there are some areas where it is important that they learn how to use this kind of new tools, right?
Say they shouldn't do something, they should, by all means, they should do everything. But I'm just saying, if many American institutions to teach the first kind of rigorous math proof class you've never seen proof before, it's a challenge. You have to explain, somehow you have to explain why something is a correct proof or something isn't. And the easiest thing to have, just write it in lean. It either compiles or it doesn't compile.
Maybe just a thing I was ask about whether students should use AI, but they already use it. So it's not that we have control over it. And maybe another thing, if it lives in my mind, like this formalized mathematics and AI, they are somehow indifferent. It's like very different things. Of course, everything can be combined together, but those are like things like two very different questions.
I'm not quite following the argument, but this whole thing reminds me of my experience, bad experience with word processors. So I used to be able to write Chinese characters pretty well, but after using word processor, I cannot anymore. I think we are talking about the same kind of effect on the computer.
I think AI could be helpful to train many mathematicians who just work for routine mathematics development or engineer type things. But in order to make mathematics to really advance in the next stage, we need some creativity. And for that, we need a lot of curiosity, which largely depends on the taste of a person. Each mathematician has their own taste. I'm not sure whether AI could train some people who have some special taste. For example, George yesterday mentioned that he thinks that the greatest paper in mankind is Killing's paper on the Lie algebra. I think many of us may not agree. Some people may think Riemann's great paper was the greatest, and some people may think differently. So these are matter of taste and curiosity are built according to your own bias or your own taste. And I think AI probably would not be able to do that. It's a largely personality driven and your environment, how you were flourished from.
I think this audience will all agree that we are fascinated about mathematics and we love the curiosity of looking at new problems. You seem to have been very successful in convincing larger part of society here in China to support this curiosity. It's not true in all countries. So what should we do to install this curiosity amongst the young people? There are some studies that you have to start even below 12 years to install this curiosity in science and mathematics in young people. Do we do enough? Or can we do more? Okay.
Well, in China, we train a lot of people who are skilled engineers. And that's one of the reasons I believe that engineer and industry are doing very well in the last 10 years. We have many skilled labors compared with America or Germany or some other countries. So they are very important that we need to train these people. But in order to lead a major breakthrough in technology or in science, we need a smaller group of people who are willing to spend time to look at things fundamental and may not look useful. So my view is that we just need, say, in the order of 1% of students be trained in a more non-standard way. And this may not be trained by people with AI background.
Mm-hmm. There's some experiences from other countries about how to train young people. I know there's a great tradition in Ukraine, for example.
Just I think that somehow many people have natural love for science and mathematics. I think it's just something we can learn very intuitively as children. So I remember when my son was very small, and at some point he realized that like 2 plus 3 is the same as 3 plus 2, and this was such an amazing happiness on his face. And I think he actually got it just intuitively. And so I think that maybe as adults, our job is not to kill this spark, but to nourish it, to not to make school boring, to support children. So in my own childhood, I remember what was somehow a big motivator for me. These were math competitions.
Okay.
This was somehow something I enjoyed a lot as a school student. I know that for some people, some people don't like this kind of events. For some people, it does not work. For example, again, like my son didn't like things like that at all, but he still enjoys like science and physics and mathematics in other ways. So yes, so maybe it's not a very precise advice, and it's not clear how to turn it into a policy, but yeah, maybe it's more like a naive human one.
So I would say that everyday teaching is fine, but they want some small success. Building up a success above another, that may reach to bigger success. And when I was small, I used to be not doing anything much, but one small success experience. The teacher gave us a quiz, and if I got the quiz right, one can get a roll cake, you know. So how many people can get it? Well, they can cut it into equal pieces. And it was only that moment I got curiosity or appetite. I got it, and I was the only one. And that small success feeling remained for some time. Yeah.
Yes, actually, I was just thinking on the stage that whether, AI or when we know many things, does that help to develop our curiosity? Because sometimes I feel I become more curious about something when I have becoming more familiar with it, or I have think about it for a long time, and then I have more question about it, which wouldn't arise at the first place. So yeah, maybe sometimes spending more times on something you're interested in would already help to develop some curiosity.
Professor Mori mentioned the importance of a teacher in this role in bringing the curiosity. Professor Yao said there should be just a small percentage who get sort of exquisite training. In some other, but don't we need also some understanding and sympathy for mathematics in a broader part of society in order to ensure that the broader part of society is supporting mathematics?
For some country like China, each year we have 14 million students graduate from high school. There are enough students who can work for the society. If we just choose 10,000 billion students to work on something more pioneering, more curiosity-based, which may lead to nothing, but it may lead to something, who knows? I think this certainly we can afford it for such a small number of people. And the way that it is being structured is that everybody will take the same examinations, everybody will be trained into doing the same problem in a certain manner. In the examination, sometimes you are not allowed to use different ways to solve the problem. And the examiner would insist that you solve some problem in some way. Not like in the old days when Gauss want to construct the 17th regular gun, use 17 methods, and each of them could be interesting and useful. And this is, I think, is not dynamical. I think we should allow in the order of, say, in the case of China, in the order of 10,000 students who are allowed to roam around in their way of thinking and give them basic training, and yes, should be able to create and go to many different fields. I think certainly we can afford it. Mm-hmm. There's no contradiction to have a large number of people just working in a routine manner. Mm-hmm. It's fine. Well, I mean, my son, for example, is actually very creative in biology. But when I try to teach them mathematics, he doesn't care too much. He just thinks in a routine manner. He was good in that, but not excited by the subject of mathematics. For this kind of students, they could go to different fields, maybe even in business, in law, in different subjects. It's fine.
No, I can't say. I can't say how things should be, but I can maybe tell you sort of something I would consider to be a dream. And I think a very important, very important mathematics is not what we, what's the problem we consider or what's the conclusion we draw, but how we approach the problem. What we consider to be the input to the mathematical problem, what we consider to be the output. And this is to take the right point of view is sometimes much more important than to do any kind of technical manipulation. And I would, in some dream world, we would communicate that knowledge to much broader audience than it's currently communicated. And specific example, this is really coming from the heart. And so people, whatever kind of three-dimensional engineering you do, you're doing whatever, quantum mechanics, you're doing electricity and magnetism, something, you will see the good old spherical harmonics, Legendre polynomials. And as a representation theorist, I must tell you, every time I see how this is handled by engineers, I just cry. And so if we could somehow communicate to people who really need these functions, how you think about them, and there are many such examples, that would be great. Yeah.
And maybe as we are sharing dreams, so maybe I have another dream, is if everyone who goes to school and studies mathematics actually learns what is the concept of mathematical proof. Not in the sense that people should try to prove Riemann hypothesis, but just to understand what proof means. And actually we have a great way how to do it, right? So all this like the geometry written by Euclid, it still exists. And it's, when I went to school, we studied this at school, so it's possible to do this at school. And I think this was a tradition which at some point got somehow lost or forgotten. At least I don't see somehow it, when I look at my son's homework, I see that. And I think this is something which many people could understand and enjoy, and this probably even could make our society a bit better.
I agree with you. I mean, my dream for Germany would be that in each high school, there is one teacher who has the ability to really understand some mathematics and bring it to the most gifted students of his high school. That would be one dream. Maybe we share our dreams.
So I think everybody is different, and somehow, in my case, I'm interested in things which other people don't get. So just following my curiosity, I have been doing a problem which later people got interested in somehow, not the other way around. And it has been this way for more than 70 years, so I cannot change.
So you mentioned how important to have a good teacher in a school. So I disagree with that. At least in my case, when I went to high school, I think my parents sent me to the worst high school in town because that was only school where I had a chance to enter. Because there were some, at that time there were you have to be working class or something in order to enter high school. So anyway, anyway, and this high school, the mathematics teacher was terrible, just terrible, knew nothing, and it was very good for me because I decided to study from using some mathematics magazine. So I spent all my time studying by myself, and I think it was much better for me. Yes.
But maybe this is just the best medicine for George Lusztig and not for everybody else, right?
Yeah, that's true. But I talk about high school, yes. Yes.
Right. Concerning mathematics, what are your dreams in that direction? What are the visions? Just short words.
Needs to be changed to the extent that we can deal with quantum mechanics. And this, of course, exactly what people in theoretical physics like to do. But we probably can look at it from our point of view to have a geometry that can cope with quantum mechanics. And this is exactly what Riemann said actually in his famous address. He wants to see a geometry which can deal with very, very tiny region and also very, very large region. Many people did not read Riemann's first paper. And this paper has many, many ideas about space-time, which in many ways already tackle the problem in general relativity. The one of the greatest paper, I think it's better than Curing's paper.
Any dreams?
Yes, my field is algebraic geometry, and it combines algebra and geometry. And algebra is digital, geometry is analog. So I take best part of both. I think algebraic geometry is best for me in that sense.
You? Mathematical dreams?
Yeah, so find solutions to some problems I'm thinking about. So maybe I work in number theory, and number theory it's like an umbrella term for almost anything. So yeah, so maybe so I don't know, maybe like learning more things. And, so maybe I'm still like learning and searching for the perfect dreams.
Okay. Sorry? Right. Good idea. Are there some questions from the audience to the panel?
Okay, thank you. So I have a simple question.
would like to ask our panelists. Which special aspects of your research fields attracts you most? Thank you.
Which specific aspect of your research field attracts you most? Maybe I start with an answer. For me, it's the combination of geometry and analysis in physics. When, for example, in general relativity, three things come together: physical intuition, geometric models, and then analysis in order to prove theorems. That's sort of the fascination for me. Some other?
I think I like the structures in representation theory and also the connections to many other fields. That's the thing which attracts me a lot.
For me, I think it's a simple principle that can give us a deep understanding of some part of mathematics is exciting. That's how I was so excited by the Calabi conjecture. The statement is simple, and it was able to create many interesting universe or space, and that have deep into the nature of geometry. I found that extremely fascinating. That's why actually, when I was a graduate student, I prepared to work on this problem than Riemann process when Chen asked me to look into Riemann process. And I feel that it's far more exciting. Once I got excited on it, I actually put in full time to try to learn it, how to do it. I bring this same thing as to my friend, Richard Hamilton, when he's strike gold by looking into the rigid flow, and then he wanted to solve every problem by rigid flow. And he succeeded to a large extent.
There was some other question also in the audience.
Hi, my question is for Professor Wielzowska and Professor Shan. As female mathematicians, what's the most challenging thing you have in your study and career journey? And what suggestions do you have for female students who like math or will not take it as their career? Thank you.
Yeah, so maybe a difficult thing for me was actually traveling to follow my job. So that's probably also difficult for male mathematicians or mathematicians of any gender, but I think that maybe for a woman this is a bit more difficult, and yeah, so I don't know what would be a remedy for that, and I think a very important thing is the support from, at least for me, very important for me was the support from my family, so that my family helped me to go through this journey, not only scientific, but often also very like physical journey through the, from country to country. And just so again, as I told you, I don't know what is the remedy to this, so maybe things have to be like that, but and then of course to for other female mathematicians, what I could say is just to encourage them to follow their dream, to do somehow not to give up, and to believe that at the end everything will be good.
I think, how to say, so there is some biased opinion from maybe more like people outside of math of thinking like perhaps like males are better for doing math and females, they have some characters, it's not good, and well, it's not adapted for math. And then I think about this question for some time, and then I came up with this idea, I think, is just, like in some languages, there are words which are masculine and their words are feminine. And when you're doing math, there are certain characters which we can say that, call them masculine characters. Like, I would just do some example like persistent or some strength, or like, it's good for doing math. But there's also some feminine characters, which people think of feminine characters, which like being patient or careful and this kind of things. And I think it's just as human being, everyone, it's better to have more characters. It's better to have both masculine and feminine characters, and that both helps for doing math. So I think girls should be confident on themselves, and if they're interested in math, just go ahead.
Are there other questions? It's over there. Oh, here. It's okay.
Hello, thank you for sharing your dreams with us. I just wondered, with the advent of quantitative finance, do you see the flow of talent away from academia to finance? Is it a thing? Thank you.
Are we losing mathematicians towards finance?
I was chairman in Harvard University about 15 years ago. Many of the investment firms in Wall Street called me to try to recruit the students from Harvard in math department to go to financial market, offering a huge amount of money. I refused to help them, and then finally they asked me whether I would go, and they offered me $2 million per year, and I turned it down in the phone. So it depends what your interest is. I don't believe that all exciting mathematicians who are excited by mathematics will go to Wall Street. Only a small number will go, but not all of them. But of course, some of them are extremely successful. Jim Simons was my friend, and he made a tremendous contribution back to the mathematics community, which I admire very much. But Jim Simons always interested in mathematics, even a few years before he died, which I admire very much. But he did make important contribution in mathematics before he went to Wall Street. I don't think financial market or financial investment will make much difference for us. I was told that Gauss was also interested in investing. That's how he created statistics and many different subjects. No problem.
Thank you.
I think we have time for another question. Yes, over there.
Yeah, so I would like to ask, like, when you tackle a difficult problem, how to make yourself motivated and when you get stuck?
Who wants to answer?
So maybe one way I try to, I think I read it in some books, if you find a problem and the problem is very difficult and you get stuck, then maybe it means that the problem is truly challenging. So when you will finally solve it, the regard will be really, really great.
So if I'm given a difficult problem, and if I get interested in, I spend hours and hours. I know a friend of I know someone who can think any problem, but only up to 1 hour. In my case, I don't mind working hours. But when I found something try not to, in the evening, I try not to think further. I take a memo and go to sleep, because if I kept working on it and found a mistake, I will never be able to go sleep. So that's the best way to keep working.
Thank you very much.
Well, there's a question, what level of stuck that you get into? If the stuck is rather superficial, you can always come back fast and quick. Maybe after an overnight sleep, you can wake up and go overcome that. But when you see how tough the problem is, when you got to a point that you see is hopeless, then you probably need to think about carefully, maybe you're going in the wrong direction. When a problem is solved, you really do not know which side is right or which side is wrong. You have to make a choice whether you should go this direction and go in the opposite direction. And that's what happened to me. After 3 years trying to prove the Calabi conjecture, I got defeated so badly because I tried to give a counterexample, and I worked really hard on it, and then I found out it's hopeless, difficult. And then I asked myself, maybe I go in the wrong direction. And then I go reverse way and succeed after 3 years. But that still takes 3 more years to do. And I learned the similar thing that happens to many outstanding problem solvers. Leonard Carlson tried to solve the Lucene conjecture, and he worked on it for many, many years, maybe more than 15 years. And finally, he found out he got stuck in a very sensitive way. He told me that he found out he should go in the wrong direction, go in the opposite direction, and then he solved the problem. So it really depends on the level of stuckness. If it's serious, that you try all kind of method, you still got stuck, then maybe you are not working in the right direction.
Thank you. And it's getting late, and Professor Yao told us how important it is to have a good night's sleep, and we still have a wonderful performance to expect. And therefore, it's now time to thank you for your interest and to thank the panel for the many interesting discussions. And I think we should, in particular, thank Professor Yao for setting up this evening and let us have this discussion here at the ICBS. Thank you very much.
Thank you for all the professors. Please be seated in the audience and have a rest. Thank you. It's really a deep and profound discussion, which inspires us a lot. I believe the past